In this section of notes, we will be looking at binomial random variables. So we're going to show you kind of some shortcuts here for how to work with one specific situation. This is a situation where you're going to be repeating the same process over and over again. And if you meet these certain criteria, rather than doing longer stretched out calculations, you can kind of shorten your work. So one example of this might be saying, let's say someone is an 80% free thrower and you want to find out what's the probability that they take 5 shots and they make exactly 2 of them. Or what's the probability that they take 5 shots and they make 2 or more of them. Or what's the probability that they take 5 shots and they make 3 or less. So these are the kinds of questions you'll be able to answer with these formulas. So the first thing you have to do is you need to check to make sure that you're in a binomial setting. And there's 4 things you need to check for. The first thing you need to do is you need to check that your situation is binary. So there's only 2 outcomes. It's either success or failure. Now, depending on the problem, you might be able to redefine it. So for example, if I say you're going to roll a die, well, at first that doesn't seem binary because there's 6 outcomes, but maybe I'm going to say something like, what's the probability that you roll a die 3 times and you get 2 even numbers? Well, then that is binary because when you roll a number, it's either even or it's not even. So it could be binary. So that's the first thing we need. We need the situation to be binary. The second situation is that we need the trials to be independent. So knowing what happened on the first one is not going to impact what happens on the second one. So something that would not fit into this category would be maybe picking something out of a hat without replacement. So like if you had a hat filled with 100 red and blue beads, and then when you say, well, what's the probability the first one's red? What's the probability the second one's red? The fact that you took a red one out on the first try is going to change the probability on the second one. So if you're doing something without replacement, it's not independent. The next thing you need to check is that there's a set number of trials. So you're going to say in advance, I'm going to have the basketball player take 5 shots. I'm going to flip the coin 10 times. I'm going to pull 8 beads out of the bag, something like that. So you need to have a set number of trials. And then for successes, we need the probability of success to be the same on each trial. Now, at first, this sounds like it overlaps with independent a little bit, but an example of where this would be different would be, let's say maybe you were taking a test where you have never seen any of the information before, and question 1 is multiple choice with 4 choices, so you have a 1 in 4 chance of guessing the right answer. But then question 2 is true-false. Now you have a 50% chance of getting the correct answer. Those 2 questions are independent, but they don't have the same probability of success. So we use the acronym BINS, B-I-N-S, to help us remember to check these 4 things. Anytime you meet those 4 things, you can move forward with this process. So if those 4 things are met, we have a binomial setting, which means that we have a binomial random variable. And if we match those outcomes with our probabilities, then we have a binomial distribution. So let's look at an example. Let's say that we have 2 parents and they're going to have 5 children, and the probability that any specific one child that they would have would be 25% that that child has type O blood. And we want to find out what's the probability that they end up having exactly 2 children with type O blood. So first we check our bins. So it's binary, the child either has type O blood or it doesn't. It's independent, the probability that one kid has type O blood should not impact whether or not the next kid has type O blood. There's a set number of trials because we're going to have exactly 5 children, and the probability of success remains the same every time. It's always 0.25. So here's one way that this could happen. They could have the first 2 children have type O blood, and then the second 3 not. And that would be the corresponding probability. However, in terms of the arrangement, maybe they have the children in a different order. So if we want to think of every possible order where you could have 2 successes and 3 failures. And it turns out that there are 10 of them. So we're going to take our solution from before and multiply it by 10 because there's 10 different outcomes. So this is kind of the longer way to go about doing this problem. What we can do to kind of shorten our work a little bit, instead of figuring out every possible combination, so we figured out there'd be 10 combinations, we have a formula for that will allow us to figure out how many combinations there are without writing them all out. And you may have seen this in a previous class. The coefficient piece, like how we would know to say multiply by 10, would be this part right here. You may have seen this written as NCK or NCR. So this second variable, sometimes depending on the resource you were using, it might be something different. Usually the N's pretty standard. The N is the number of trials, and the second letter, sometimes I've seen it as a K or an R or an X. That second number is your number of successes. This is our formula, and remember the exclamation point is called factorial, and it means you start at that number and then you multiply all of the numbers down to 1. So like, for example, 4 factorial would be 4 times 3 times 2 times 1. There is going to be a separate video later on how to put this into your calculator so that you don't need to do this whole formula. You would just tell your calculator what are these 2 values, how many are you picking from, and how many successes are there, and then it would give you that value for the coefficient here. So we already did this by hand, but once you see the calculator video, you could do 10, or sorry, I think it was 5. It was 5 children. 5 children and choose 2 of them to have type O blood. You could put this into your calculator and it would give you the 10 combinations that we manually found previously. So now we're taking that coefficient and we're plugging it into the rest of our formula. So we take the probability of success raised to how many successes there were. So 0.25 is the probability of type O blood squared because we want 2 kids to have type O blood, times the probability of failure. So 1 minus p raised to the number of failures. In that case, it was 3 failures, 3 kids that did not have type O blood, and then multiply by your coefficient. So this formula is on your formula sheet, but you do want to know what the variables stand for. The one thing I will mention is that on your formula sheet is that it uses an X rather than a K. So if you would replace all of the K's with X's, it would look exactly like what's on your formula sheet. So let's go back to that example about the children and having type O blood. And we want to look at how we would do this. So there's going to be 2 methods. Number 1 is going to be using this new formula we just came up with. And then number 2, there's going to be a second video for you to watch. And you're going to use functions called binom PDF and binom CDF. And make sure you pay attention to when you use which one as well. But we'll do the by hand one for first. So going back to that same example, if we want to find the probability that they have exactly 3 children with type O blood, we're going to have 5 children. We're going to choose 3 of them to have type O blood. Probability of success is 0.25, and we have 3 kids that we want to have type O blood. Probability of failure would be 0.75, and we'd have 2 children who would fail or not have type O blood. That gives us this value. Now let's say we wanted to find the probability that we have more than 3 children with type O blood. Well, in this case, that would mean 4 or 5 children. So basically, you have to do that process we just did above, but you have to do it twice. You have to do it once for 4 children and once for 5 children, and then you add those 2 probabilities up. Now, the second part of the question for part B is, should they be surprised? Remember that we kind of have a rule for this, and you don't really get to determine whether or not you're surprised. The rule is, if it happens less than 5% of the time, that's surprising. It's statistically significant. It's unusual. It is convincing evidence. Those are kind of things that we use interchangeable for surprised. So since there's a 1.5% chance of them having more than 3 kids with type O blood, that would be surprising because 1.5 is less than 5%. So make sure you watch the 2 videos on how to do binomial distribution calculations on your calculator, and then try the practice problems.